maybe I'll just give it to the end of the minute and then kick us off. Okay, maybe I'll start there. Okay, welcome everybody. Welcome to the 30th ECS and Cloud Feedback Virtual Symposium. Thank you to everyone really for making this event such a wonderful experience. It's, thanks to everyone who's spoken over the years and to all of you guys for coming. And just everyone for making this great thing. So today we have three really great speakers. And we're just going to go over some sort of ground rules for the symposium, how it works. So we're going to have 3 12-minute talks. After each talk, there'll be a few minutes for questions. And if you have any questions, you can type them as comments directly into the chat. And one of us will ask the question at the end of the talk, or you can raise your hand and then we will unmute you and you can ask the question directly. And if there's time after all the talks are over, we'll have a short general Q&A at the end. If you would like to give a talk in the future, please contact a member of the executive committee. You can find our contact information as well as all sorts of great information like videos of past talks and ways to sign up for our mailing list at our website here. And let's head over to the first talk. I'll stop sharing your screen. Our first speaker today is going to be Antonietta Capotondi, a research scientist at NOAA Physical Sciences Laboratory and at University of Colorado series. And I'll let Antonietta bring up her slides.
If I can.
No worries.
Fine. Oh, yeah, it is. Okay. And it's already in full screen, correct?
That's right. Excellent.
Okay, perfect. Thank you very much. Okay, well, thank you so much for the invitation to participate in this symposium. So it's really a pleasure to be here. And thanks everybody for attending. So I will be talking about tropical Pacific decadal variability, and most of the material that I show comes from this review paper that was just published a couple of months ago, which is the result of activities of a CLIVAR working group on tropical Pacific decadal variability. So, oops, of course, during the presentation, it never works. So why do we care about TPDV? So we know that TPDV modulates ENSO characteristics and its impacts. Also, we know that it can affect the global climate, for example, by modulating the rate of global warming. I think for this audience, it's also important to, important to understand TPDV because it can provide guidance in separating the internal variability from the forced climate change signal, and also to provide guidance to assess the model's fidelity in the simulating tropical dynamics. So the review paper covers many aspects of TPDV. Today, for brevity, I'll focus on 3 different aspects. I'm going to look at the surface and subsurface characteristics of TPDV, so patterns are important, and just discuss mainly the leading ocean processes and our current understanding of their interaction and relative role. And then briefly, if I have time, I'll kind of discuss the possible origin of the atmospheric forcing of those processes. So how does TPDV looks like? So one way to characterize it is by conducting a UF analysis of detrending. So, and I'm focusing here on the internal variability. So conducting a UF analysis of detrended and low pass filter sea surface temperature anomaly over the tropical Pacific. So the leading principal component is then defined as the TPDV index, and we can use linear regression to determine the pattern over the whole basin. So if we compare this pattern with the ENSO pattern, which is shown here on the right, we see that they are similar. So in fact, we have known for almost 3 decades that TPDV is ENSO-like. However, the meridional scale of the anomalies in the tropics is broader, a decadal time scale. There is a larger loading in the North Pacific. And unlike ENSO, whose anomalies tend to be larger in the Central Eastern Pacific, TPDV has the largest anomalies in the Central Pacific. So these anomalies, this pattern that we can detect with UF analysis is very similar, is very consistent with what we find just by looking at decadal phase transition. So the figure here in shading shows the sea surface temperature differences between a cold 1999 to 2014 minus a warm 1984-1999 decadal epochs. And the contours show actually the sea surface temperature pattern that we have determined before through UF analysis. So we see that anomalies in the tropics tend to be associated with anomalies of the opposite sign in the central and western mid-latitudes. TPDV is associated with changes also in atmospheric circulation, which is illustrated here by the sea level pressure in shading and the surface winds indicated by the arrows. So these are the differences between these two epochs. And for this warm to cold transition, we have this enhancement of the equatorial trade winds, both in the off-equatorial and also along the equator. So changes in the winds can be expected to alter the ocean circulation and also alter the upper ocean heat content. And this can be inferred by looking at the differences in sea surface height, which is shown here. And sea surface height is a quantity which is dynamically linked to thermocline depth and also to upper ocean heat content. For this particular transition from positive to negative, can you see my cursor?
Yep.
Oh,
yes.
Perfect. Yes, for this transition, we see that we had large SSH anomaly in the Western Pacific with maxima, which are actually located off the equator in these two areas of the equator, and then anomalies, weaker anomalies of the opposite sign in the Central and the Eastern Pacific. So if sea surface height is associated with its content changes, how does this content changes look like? So what we see here is the temperature difference between the negative minus positive phase, average west of the dateline and shown as a function of latitude and depth. So the interesting thing to notice is that these anomalies actually are below the surface and are located at the depth of the main thermocline, which is identified by these three isotherms. And the anomalies, the large anomalies in the thermocline tend to be an indication of vertical, or maybe in this case also latitudinal displacement of the thermocline as typical of wave activity. And we will return to this point later. But another point that I would like to make is that these large areas of large SSH and heat content of the equator have also emerged as possible sources of decadal predictability and prediction skill. So in the Eastern Pacific, the heat content tend to be weaker and tend to be surface intensified. So this pattern of SSH differences is for the trended anomalies. So this is reproduced again on the left. If we don't detrend the data, we see that there is clearly the anomalies are much larger, especially in the Western Pacific. So this is associated with this large increase in sea level in the Western Pacific that the large literature has discussed. And however, what we can see is that the pattern is similar. So this lower frequency evolution, the lower frequency changes, which may be due to climate change or a lower frequency mode of variability, it looks like they have similar pattern. And so this suggesting that they may be due to similar oceanic processes. So what are the oceanic processes? Here on the left, I'm showing the climatological conditions of the tropical Pacific. So on the top panel, the top part of the figure shows the zonal currents, the surface winds, the low latitude western boundary currents, as well as depicts also the Walker and the Hadley circulations. While in the lower panel tries to provide a more dimensional view of the ocean structure. And in particular, an important feature of this structure is these convective cells, which are known as subtropical cells, which have been invoked in some of the main theories of TPDV. So these cells are characterized by a subduction branch in the subtropics, an interior equator flow in the thermocline, and then equatorial upwelling. So the main mechanisms that have been proposed for TPDV can be categorized in this, shown here on the right. So the first one is become known as the V-bar-T prime hypothesis. So this means that mean velocity climatological STCs can affect temperature anomaly from the subtropic toward the equator, where they can be brought to the surface by the upwelling and affect equatorial sea surface temperature. To be transported as a passive tracer, these temperature anomalies must be density compensated by salinity, and that's why they are called spiciness anomalies. The second mechanism is known as the V'-T-bar hypothesis. So even in the absence of any temperature anomalies, just changes in the circulation can lead to a change in the upwelling, which can result in changes in the equatorial sea surface temperature. Increased upwelling will bring more colder water from the subsurface to the surface, cooling the equatorial sea surface temperature, and vice versa for decreased upwelling. Of course, changes in the wind also cause an ocean adjustment to Rossby wave propagation, which in itself introduce a delay, introduce an adjustment timescales. In fact, several studies that have discussed TPDV in terms of advection of temperature anomalies that were not compensated, they were actually discussing or illustrating wave propagation. So if a temperature anomaly is not density compensated, can propagate as a wave. So we are going to revisit this mechanism in a little more detail now. So of course, the description of the subtropical cells as just a simple overturning cell is very idealized. In reality, they have a much more complex three-dimensional structure, and this figure tries to illustrate that by looking at the depth of an isopycnal, which is in the core of the main pycnocline. So for the V-bar-T prime hypothesis, we have the spiciness anomalies, which from the subtropical region are brought by the mean circulation toward the equator, and then at the equator, they are upwelled toward the surface. So can this mechanism work? So there have been several studies trying to demonstrate it. A recent study actually used the ocean model and backward trajectory to identify possible pathways by which spiciness anomaly can reach the equator. So spiciness anomalies tend to be formed in the eastern subtropics, like these dashed boxes, and then they tend to move more easily from the southern hemisphere. I forgot to say that here there is this ridge in the pycnocline depth, which is known as potential vorticity barrier, and is associated with the presence of the ITCZ, and this makes the flow much more, the pathway from the northern hemisphere much more convoluted for the anomaly. So here, most of this anomaly from the northern hemisphere tend to go to the western boundary. So pathways are found. However, a heat budget analysis along the equator seems to indicate that the spiciness anomaly has a small impact on equatorial sea surface temperatures. Also, observational studies show that there is a large level of mixing, especially in the near the western boundary, which could dissipate the spiciness anomalies they propagate toward the equator. So at this point, the feasibility of this hypothesis is in question. Now, the second hypothesis, instead, as I mentioned already before, involves a strengthening or a changing in the velocity of the STC, the isopycnal velocities. And this hypothesis has been explored in many different studies, both observational and modeling studies. And all of these studies have shown a large correlation between the changes in the velocities, the changes in the transport, and the equatorial sea surface temperatures. So this is an example for a recent study that I did. And on the left panel, we see the mean meridional velocity. The study used the ocean reanalysis, the Goddard ocean reanalysis. So the mean meridional velocities at 9.5 north and 9.5 south. So you can see that in the top 50 meters, there is poleward flow. This is the surface Ekman layer, and then there is equatorward flow below that surface layer. So one can compute the equatorward transport by integrated. In this case, I integrated from 300 meters to the bottom of the Ekman layer, and then zonally across the basin, excluding the western boundary currents. So on the right, we see this transport at 9.5 north and 9.5 south. But what is important for the equatorial sea surface temperature is the convergence of this transport. So the transport at 9.5 south minus the transport at 9.5 north. This is shown in this third panel by the black line, and it is compared with the equatorial sea surface temperature evolution, which is shown with the sign reversed, just for ease of comparison. So clearly there is a very large correlation between these two time series, so really indicating that there is a strong connection between the transport convergence and changes in sea surface temperatures. And this good correspondence is found both at interannual time scales, but also at decadal time scales. So this is all good news. It just supports this idea of the V prime T-bar hypothesis. However, the largest correlation are found at zero lag. So this calls into question any causality between transport changes and sea surface temperatures. So how can we explain this correlation? So the explanation relies in the ocean adjustment. So these transport changes, in fact, appear to result from the ocean adjustment through Rossby wave propagation. So as the Rossby waves propagate westward, they alter the zonal slope of the thermocline or the pycnocline, and they, by geostrophy, you create a meridional, resulting in a meridional flow. And this can be, in fact, demonstrated relatively easily by using a simple 1.5 layer shallow water model, which is in practice a Rossby wave model. In fact, CR is the phase speed of the long Rossby waves, WE is the Ekman pumping forcing, and then there is a dissipation term. So this can be...
Sorry, Antonetta, just to say, maybe a 2 minute,
okay.
2 minutes more. Thank you very much.
Okay, I think I'll be done in 2 minutes. And so one can integrate easily this equation, and and then we can display the resulting sea surface height anomaly as a function of longitude and time. And as you can see, this sea surface height derived from this model compare very well with the sea surface height from the ocean reanalysis itself. But most importantly, if we take the gradient of this sea surface height anomaly derived from the model, by geostrophy, the transport, integrated transport is proportional between two different longitudes, is proportional to the sea surface height gradient between those two longitudes. We find that this red curve, which is this transport deduced, inferred from the sea surface height from the simple model, compares very well with the transport that we have that can be calculated directly from the velocities. So this adjustment process to Rossby wave propagation is a key component of the PDV. These Rossby waves are responsible for those sea surface height maxima in the western of equatorial Pacific and for also the STC transport changes. However, the wave transit, so the transit time of one wave cannot account for the decadal time scale. So, so this adjustment need to involve many ways, maybe over a broader latitudinal area. And this is most of what I wanted to say. If I have 1 more minute, I just wanted to discuss very briefly the origin of the anomalous wind forcing. So of course, these ocean processes are forced by the winds. And so the question here, where do these winds come from? One possibility that they respond to decadal equatorial sea surface temperature anomaly, producing like a feedback loop, but which has been proposed by in some studies, but it's very hard, especially in observation, to clearly demonstrate these feedback loops in the presence of a large level of atmospheric noise. Also, there has been suggestion that influences from other tropical basins could lead to wind forcing at decadal time scale. For example, the tropical Pacific cooling starting toward the end of the 1990s was associated with the Atlantic warming. However, there is still also in this study, there is a large uncertainties also because these numerical experiments are very delicate to conduct and may lead to an overestimate of the Atlantic influences. And finally, there may be influences from the extratropical Pacific, which are also enhanced by tropical extratropical interaction, and they involve very meridional modes dynamics. And there are some recent findings that seem to support this possibility, but this is still an active area of research and needs more work. And I think that's all I would like to say. Thank you.
Thank you. Thank you very much.
Should I stop sharing?
No, you can keep it up for a second in case people have questions, I guess. Yeah, if anyone has a question, feel free to raise your hand and chip in, or you can write in the chat and we'll read it out.
Maybe I can make some conclusion there.
I suppose in the meantime, maybe while people are still warming up, one of the questions I had is, so most of this is with like reanalysis, I think. Do you have any sense of whether, say, like CMIP models are particularly good or bad at reproducing certain mechanisms that you can identify?
Yeah.
Reanalysis, so like the equatorial undercurrent and things like that.
Yeah, so that actually there have been some studies done on the equatorial undercurrent, and I think there are still biases in the model. There has been also a study that have specifically looked at this relationship between the transport and the sea surface temperatures anomalies, and some models can reproduce these correlations, but others don't. And in any case, it just seems like the sea surface temperature, so the models seem to underestimate the transport convergence. So for the same sea surface temperature difference, I think there is a smaller transport convergence, suggesting that the sea surface temperature in the model may be oversensitive to these processes. So most of the analyses have been done actually in kind of more of statistical way. I don't think that anybody is really like tried to implement a Rossby wave model on a climate model. I think that's actually something that I would like to do to really better understand what the tropical dynamics is in these models.
Interesting, thank you.
That's a good question.
I think in the interest of time, we should probably move on to the next speaker, but we'll hopefully have some time at the end of the session as well, where people can ask remaining questions.
Sounds good.
Thank you very much.
Thanks.
Thank you again for that great talk. And our next speaker will be Daeho Jin. Daeho is a research scientist at NASA Goddard. And maybe if you let, great. Excellent, I can see the slides. Great, take it away.
Hello, my name is Daeho Jin. Today, I'm presenting ENSO disrupts boreal winter CRE feedback, which has just been published in the Journal of Climate. Oh. I'm sorry. Okay. The assessment of radiative influence of cloud is important to understand the global warming. In this study, we focus on CRE feedback based on 20-year satellite observations of cloud and radiation. Particularly, we analyze seasonal CRE feedback because ENSO heavily affects global cloud distribution, and such ENSO activities are seasonally asymmetric. I'm happy to show these figures from my paper 14 years ago. The left figure shows the strength of ENSO represented by the linear 3.4 index, peaking in DJF. And right figure shows the ENSO responses to SST and geopotential height at 500 hectopascal are also seasonally locked. For radiation, we use the series FBCT product, level 3, total flux at 1 degree and daily resolution. And we use meta-2 reanalysis data for surface temperature. And our domain is 60 degrees south to 60 degrees north for 20 years. The CRE feedback is defined as the change of CRE by the change of mean surface temperature. And this alpha, in this study, this alpha is obtained from the linear regression of CRE against surface temperature. This figure shows yearly distribution of seasonal mean CRE and TS. Short wave CRE on the top, long wave CRE on the bottom. Left side shows DJF and JJA is on the right. Now the center column is screened out because it is a spoiler at current stage. Comparing DJF and JJA, we can see that JJA shows stronger feedback signals by comparing the slope values. And in the case of long wave CRE in DJF, is less organized compared to others. For more details, we follow Zelinka et al. 2022 for the to perform a decomposition by regimes. Then what do we need for this decomposition? We need cloud regimes. We employ the modest cloud regime defined in the same domain, 60 degrees south to 60 degrees north. But a small problem is that this regime set has too many regimes to examine. So we made a few groups of these regimes for convenience. Here are total 8 cloud groups. Mostly tropical, high cloud, thick and thin. And second high, also thick and thin. Mid-level cloud, low thick, low thin, and semi-clear clouds. With these cloud groups, the decomposition shows that oceanic short-wave CRE feedback by low-thick cloud is dominant in DJF, while various cloud groups contribute to the total CRE feedback positively or negatively in JJA. Zelinka et al. Also performed further decomposition to see the relative role of mean CRE change within a group versus RFO change of a group. And this part was demonstrated in the paper, but I like to skip here to save time. And briefly saying that RFO change term is much more responsible for the feedback signals in general. So far, it is found that the dominant role of oceanic low-thick cloud in total CRE feedback is the characteristic of DJF, not JJA. Questions are, why are the CRE feedback patterns so different between DJF and JJA? And what is the effect of ENSO on these seasonal different CRE feedbacks? To answer these questions, we assess the effect of ENSO in two ways. First, examining regression of CRE against ENSO index instead of TS. And second, examining regression of CRE against no ENSO TS. First, we examine how the ENSO index is aligned with TS. This is seasonal mean TS, the distribution of seasonal mean TS by linear 3.4, linear 4, and PDO index in DJF. This figure shows that the linear 3.4 index is in good agreement with TS with high correlation coefficient of 0.674. Then how about CRE versus ENSO? In the case of linear 3.4, should have CRE is its distribution is less organized compared to the previously shown the CRE signals. Here, the correlation coefficient is just under 0.3. And in the case of long wave CRE, even the sign of slope changes from negative to positive. The same decomposition figure, but against linear 3.4, shows that the dominant signal of short wave CRE feedback by oceanic low thick clouds is actually a kind of ENSO responses, even in JJA. Secondly, we try to exclude ENSO signal from TS by using a residual after TS is regressed against linear 3.4. The bottom panel shows that DJF TS experiences large change after ENSO signal is removed. This is the same figure shown previously, and now center column shows the feedback based on no ENSO TS. And you can see that now the feedback values in DJF is similar to the JJA in both short wave CRE and long wave CRE. And with no ENSO TS, oceanic low thick cloud is just one of many cloud groups contributing to the DJF total CRE feedback. So far, our research has shown that the influence of ENSO on DJF CRE feedback is crucial. So based on this finding, we argue that JJA is a better time to examine the impact of global warming on cloud changes. This figure shows the zonal mean RF change of each cloud group for the change of TS for its latitude bands. From this figure, we can see the two major features. First, comparing purple color and orange color, and also orange and red color, you can see that cloud top of convective clouds become higher. And of course, this is already famous with the previous studies. And comparing,
sorry, just say 2 minutes. Thank you.
Comparing the yellow, green, and light blue, we can see that cumulus becomes broken clouds, mostly over ocean. So summarizing all, dominant CRE feedback signal of oceanic low-thick cloud is due to the ENSO activity. Without ENSO, DJF total CRE feedback becomes similar to that in JJA. So various clouds contribute to the total feedback positively or negatively. Observational cloud changes for TS in JJA show a hint of the global warming effect. First, convective cloud tops become higher, constant to the previous studies, and oceanic cumulus become broken clouds. Yeah. Thank you for your attention.
Thanks very much. And yeah, similar story. If people have questions, just raise your hand and you can either unmute yourself or I think you'll be able to unmute yourself with. I don't think we have to unmute you. Oh. I think someone unmuted themselves then, but I wasn't sure. Maybe briefly, I'll ask a question again then. Unless Jonah, did someone else? No. I think it's. I'll ask a very brief question. So the correlations that it was a very nice talk. Thank you, Daeho. The correlations you show are against like tropical mean TS, I think. So on the x-axis,
no, all TS is the same value defined from the 60 degree to 60 degree and all latitude weighted.
Okay. Did you see any difference if you just looked at these results in like the tropical band? I think I touched on that.
Yeah, I saw that.
Sorry.
And the if we use the local TS, then it's quite different. But at the time, it's hard to explain that the signals. So just take away. Yeah.
It's okay if I ask a quick question?
Yeah.
I'm just curious if is there reason to think that the ENSO signal itself is somewhat more pronounced in the in DGF than JJA? And I know you were showing the one of the first slides. I was wondering if you thought the difference in how ENSO is influencing the cloud feedbacks has to do with the circulation in the atmosphere, or just the fact that the SST patterns are more strongly different. And
now that I had some problem in the this the communication. Can you say again about your question?
So sorry, if I understood what you were saying correctly, you're saying that if you remove the effects, if you sort of remove the ENSO signal, then you find that removes the difference between the DJF cloud feedbacks and the JJA cloud feedback to some extent. And I was wondering if you thought this was due to the fact that maybe the SST patterns were quite different. The ENSO was changing with something about the DJF pattern, temperature pattern, or if it was due to some other aspect, something else that was different about the circulation at the time.
Yeah, it should be. But it's actually very complex problem because the ENSO response in the high latitude is there are some delays, like in some southern hemisphere is actually lead the ENSO peak, and northern hemisphere is 2 or 3 months delayed. So if you assess all the circulation, then responses, then it will be very difficult to assess this kind of problem. But now I'm assume that the low cloud, particularly the low cloud, is responding to SST near the not too high latitude, like the tropics, mostly in the tropics, subtropics, and because the now the ocean low thick cloud is a problem, and that most ocean low thick cloud in that band on the 35° north and south, and from this result, I think that with this simple method, we can screen out the instantaneous SST response by the ENSO, which can affect the regional low cloud in that area. That's the big factor, I think.
Okay, thank you very much, Daeho. Maybe if we have more questions, people should type them into the chat, and maybe we'll have some time at the end for Q&A. But thank you again for a great talk.
Sure, thank you.
Our final speaker today will be Adam Sokol, who's a graduate student at the University of Washington. Maybe Adam, get a chance to put up. Okay, great. I can see it. Take it away, Adam.
Great. Hi, everyone, and thanks to the organizers for the opportunity to talk and for continuing to organize these very fun sessions. So yeah, I'm a graduate student at the University of Washington. I'm just going to talk a little bit about part of my PhD work, which has been on this question of Anvil clouds, their radiative feedbacks and climate sensitivity. So I'm going to show some results from some this exciting ensemble of cloud resolving models today. So I think a lot of folks have probably seen this figure before, but I wanted to just show which feedback I'm going to be talking about here. This is from the Sherwood ECS assessment a few years ago. And I'm going to be talking about this Anvil cloud area feedback, which my understanding is that also kind of nominally includes changes in Anvil cloud optical depth. And what you can see here is that it's only kind of significantly negative feedback assessed in this study, and it also has the widest uncertainty of any individual feedback, cloud related or not, that was included in this report. So I think that uncertainty is not for lack of trying. There's been a lot of work on this over the last few decades, kind of going back to this original iris idea from, I guess, over 20 years ago now. So I think one kind of robust finding that's emerged from all this work is that we kind of in general expect the area of tropical convective clouds to shrink as the surface warms. But whether or not that's positive feedback is kind of a more complicated question that I'll get into what the sign and the magnitude of that feedback is. But kind of the punchline that I'm going to show is that if we kind of put any faith in these this ensemble of high resolution models, they kind of suggest the feedback is much closer to 0 or slightly positive in the multi-model mean. And that if you kind of make that change and then, add together all the feedbacks again, you get around a 50% increase in the total cloud feedback. So something that is certainly significant enough to affect ECS kind of within this Bayesian framework. So I'll kind of just briefly show the structure of these convective cloud systems in the tropics just in this cartoon. And you can see on the right, you kind of have these actively convecting cores, which are very reflective and have a high albedo. So they have a very negative radiative effect, which you can see down here. And they produce optically thick Anvil clouds that also have a negative radiative effect, and tend to thin out rather quickly at first as kind of the largest ice particles pretty quickly sediment out of the cloud. And as the clouds thin, they also spread horizontally, and their radiative effect increases and becomes positive, reaches some sort of maximum, and then as the cloud dissipates, it of course goes back to zero. So you have this compensation in the radiative effects of different kind of parts of the cloud system. I'm showing the net radiative effect here, but you can also think of this as kind of shortwave and longwave compensation is another way to kind of think about that. But kind of the total effect of this depends on the relative area covered by the different parts of these systems, right? So what I'm gonna just use thick and thin clouds to refer to kind of these portions of the system that have a negative or positive radiative effect on average. But the thicker clouds are much less abundant. The area of deep convection in the tropics is actually quite small. And the same too for the kind of thick Anvil clouds that surround active convection. But as the kind of thickness decreases, these clouds spread and grow to cover more area, which you can kind of see here as they reach their peak around an optical depth of 1 to 2. So these are satellite observations, sorry, I should have said, from the tropical West Pacific, from CloudSat and Calypso. And this is just cloud fraction kind of binned into different ice water path bins, which is the coordinate we're using for cloud thickness, which you can think of as pretty similar to optical depth. So these kind of thinner clouds are much more abundant. So in the climatological average, you get a radiative effect pretty close to zero in these convective regions. So you can kind of see from this that if you have a reduction in Anvil cloud area, that isn't necessarily going to be a positive or a negative feedback. It's going to depend on how that reduction is kind of spread across the different parts of these cloud systems, right? So our goal is to kind of try to understand physically how these systems change within this kind of cloud thickness framework, and also to assess the implications of that for radiative feedbacks and ECS. So the main tool we're using here is this radiative convective equilibrium model intercomparison project, RCE-MIP, which is this really great data set of this kind of classical doubly periodic RCE experiments on an idealized domain. So we're using the cloud resolving models, which have a horizontal resolution of 3 kilometers, and we're using a domain configuration that's large enough to allow the convection to organize on large scales into regions of ascent and large scale subsidence. And we get quite a very different degrees of convective organization across this ensemble, both in kind of the kind of base state sea surface temperatures and how the organization changes with sea surface temperature. So even though we're working with an idealized RCE here, we're really sampling a pretty wide kind of span of different circulation regimes. And we have these simulations for 3 different SSTs, 11 different models, I should say. So if we kind of look at how the convective clouds look in these models, this dashed gray line is the kind of observational histogram of ice water path that I showed before. It's just scaled arbitrarily, so you can compare the shapes here, but not the magnitudes. We're not looking if the models have too many or too few clouds. And you can see that kind of the histograms produced by these models kind of run the gamut and have all sorts of different shapes, but I'd actually think they're reproducing some aspects of the observed distribution quite well. So they put the maximum ice water path in the right kind of histogram bin in most of the models. They kind of put this ramp up in frequency as the ice water path decreases and the clouds spread. They have that in the right ice water path range, and most have some sort of peak or plateau or some sort of feature pretty close to the observed peak around an ice water path of 20 or 30, optical depth of 1 or 2. So of course there's differences here, and I think there will be, as long as ice microphysics parameterizations are involved. You're always going to get some differences between these models, but I think the basic physics of kind of the thinning and spreading of these clouds is being captured here. So to kind of understand the response to warming, we can do some averaging across the ensemble. And in the top left, I'm just showing the multi-model mean change in frequency as a function of ice water path. And below that is the CRE from before. So this positive low, but the highest ice water path is just kind of the iciest parts of the atmosphere become icier. That's from Clausius-Clapeyron and also from some dynamic contributions as well. But other than that, we really have this kind of 2 to 3% per Kelvin reduction in the area covered by these thicker convective clouds, and every single model in this ensemble is producing a negative response here. And as you can see from the shading, which is the middle 50%, it's quite well constrained by this ensemble. And I think this kind of makes sense with what we might expect from the tropical overturning circulation. We've known for, or we've expected for a long time that convective overturning slows down in the tropics. So kind of averaged over space and time, we may expect to just see fewer deep convective cores. And if these thicker Anvil clouds are constrained to be pretty close to the deep convective cores, we may expect to see fewer of those as well, or reduced area covered by them on average. So I think this kind of conceptually makes sense with what we expect from the overturning circulation. If we look down at lower ice water paths, we get a different story where the models are split 50-50 on the sign of the response, and the multi-model mean is near zero. So we kind of see that the effect of this slowdown of the overturning circulation is kind of no longer the dominant force in the cloud fraction response when it comes to the thinner Anvil clouds, excuse me. So this could reflect what we know are kind of complex microphysical and radiative processes that really shape the evolution of these clouds after they kind of are detrained and thin rapidly at first. You kind of get these maybe slower processes that take over, different circulations, maybe within the cloud or between the cloud and the environment. There's been a lot of work on those kind of recently, but I think there's still a lot to figure out. But since these things are all parameterized differently in the models, it may make more sense that we see a greater model spread there and more uncertainty in general. But when you put those two things together, what you get is kind of this overall thinning of the whole population of ice clouds in the tropics as the surface warms. And this is happening in all but one of the models. And this is pretty robust with respect to the sign of the thin cloud response. So even if you decrease cloud fraction across the board, that decrease tends to be stronger for the thicker clouds, and you still get this kind of thinning signal. And it's also robust with respect to the initial amount of convective organization or the change in convective organization. But I think the most exciting point is that there are also some observational studies that support this. You need to do a little digging to find in the details where some of these studies have separated optically thick and optically thin cloud components, but those of them that do tend to show that there is a much larger response for the thicker clouds to interannual temperature variability than for the thinner clouds. So we can kind of look at our kind of more formal cloud feedbacks within this framework. And I'll kind of just gloss over the equations here, but we kind of define this area-weighted radiative effect as a function of ice-water path. And we can decompose that as we decompose the product of any two variables, and you end up with this small nonlinear term on the right, which we can neglect. This red term here is the one we're interested in. It contains the area feedback, and also what I'm calling the bulk part of the optical depth feedback. So that's changes in Anvil thickness related to kind of uneven changes in frequency across this spectrum, as opposed to the other part of the optical depth feedback, which is microphysical, which is kind of in this blue term, and that deals with changes in the optical depth you have for a fixed ice water path. And we just don't have the output from RC MIP to kind of separate these three different contributions to the blue term. But most of what we're interested in anyway is in this red term. So this is what the feedbacks I show are all this red term here. And we can kind of compute that term as a function of ice water path. And if you just take the area under that curve, you can get your domain average feedbacks, basically. So when we do that, we get something that's positive around 0.09 watts per meter squared per Kelvin, with a decent amount of spread, but about 3/4 of the models are giving us a positive value there. And we can decompose that into the thick and thin cloud components. So the thick cloud changes, as you can see down here, this preferential reduction in the most reflective clouds gives us this big positive feedback signal. So that's what's giving us most of the magnitude for this feedback. Most of the intermodal spread and the uncertainty is coming from the thin cloud response, which is not surprising considering the models were much less certain in how the area of those clouds were changing. We can also decompose that into the more traditional area and optical depth components. So the area component is very close to zero in around 2/3 of the models and in the multi-model mean. It's the optical depth component that's really giving us the magnitude again, and also a lot of the spread. And really what the optical depth feedback is in your model really depends a lot on what the thin clouds are doing. So again, everything kind of points to needing to reduce uncertainty in these kind of thinner cirrus cloud changes. Oh, yeah. So I'll note again that a big caveat here is that our microphysical changes are not accounted for in this optical depth feedback. So that may introduce even more uncertainty, I'd expect, if we were able to account for those. So to kind of do this exercise of seeing how things affect ECS, we have to convert this kind of idealized RCE feedback and make some assumptions to convert it to a global mean. So we're assuming this is representative over tropical oceans, and I think that's hopefully not a crazy assumption considering that convection is organized in these runs. So we do have both ascending and subsiding regions within this domain. We account for polar amplification and also the low cloud overlap in this kind of framework is based on the climatology from each model. It's a little bit complex, so I won't get into it, but that's also a kind of source of more uncertainty as well, or how realistic this overlap term is in this domain configuration. But when we account for these things, we get a global mean feedback estimate of 0.03, but really pretty close to 0 when you consider the kind of standard deviation of the models, which is about double that mean value. And I'll just know that the full range of the models goes from negative 0.05 to about 0.2. And if we consider that in the context of the previous assessment, we see that none of these models are producing anything close to the strong negative feedback that was incorporated into that assessment. So I think we're getting a strong hint here that that feedback is closer to 0. And that's where we kind of came up with the value I showed at the beginning of something that's just slightly positive in the multi-model mean. So we can kind of plug that into the ECS code, and we're using all the different lines of evidence here. And what you get, as you may expect, is a positive shift in that curve of around 0.3 degrees. You also get around a 10% widening of that likely range, the 66% range or so. Yeah, so the uncertainty that we kind of plugged in here, 0.06, seemed a little low to me to just use the standard deviation, considering we have these unaccounted for microphysical effects, low cloud overlap and such. So we tested some much larger uncertainty values. We did the full model spread, and we also just plugged in the new mean value, but with the Sherwood et al. Uncertainty of 0.2. And basically all those curves look the same. So it's really the change in the central estimate that's making the difference here, as you may expect. And we are not finding too much sensitivity to what the actual standard deviation of the Gaussian estimate is. So to just kind of wrap up, I know we're about 10 o'clock, but so these kind of high resolution models are producing a pretty robust thinning of the ice cloud distribution, with warming. I think this can be reconciled in a straightforward way with our thermodynamic expectations and our knowledge of how these cloud systems evolve. And I think some detailed observational analyses support this. But in general, I think this kind of response is pretty tough to reconcile with a large negative Anvil cloud feedback. Another takeaway, I think, is that changes in optical depth are worthy of more attention going forward. If we really want to continue to constrain this feedback, I think this assumption of fixed Anvil cloud opacity won't be appropriate for really kind of reducing the uncertainty range further and further. And lastly, I think I said many times throughout, but a lot of kind of signs are pointing to our need to focus on thin cloud changes and what affects their response to surface warming and kind of what controls their area in general. It seems that these kind of large-scale changes in convective mass flux are less influential when it comes to the thinner parts of these cloud systems than they are for the optically thicker components. Yeah, so I'll leave it there, and maybe we have time for a question or two.
Thank you, Adam.
Yeah, that was awesome.
Thanks.
We've got a couple of minutes left, and I think, oh, Martin has raised his hand. So yeah, just unmute yourself, Martin.
Oh, will that work?
Yes, yes.
You can hear me and see me, maybe. I'm not sure if it worked. Yeah. So that was a very interesting assessment, and I think it's quite a little shocking almost that you go to zero feedback from the assumptions that are quite different. I have two little things. One thing on this figure, why do we see, or what might be the reasons for this large uncertainty for the lower ice water paths, so this large gray area on the left side? And the second question, the diurnal cycle. We have a big balance between long wave and short wave. And the diurnal cycle might kill some clouds a little bit on daytime. And so there will be some differences between day and night, and if you have investigated that. So those would be my two little questions, but very nice.
Thanks. Yeah, so first question was just about the uncertainty range here. So I think, well, I guess I'll start at the top. I think the uncertainty when it comes to changes in area are going to be affected by kind of these like slower cloud maintenance processes that we think happen in thin cirrus. So we know these clouds undergo radiative heating that can loft the cloud against sedimentation. There may be some circulations. I think it's still a little unclear how important these kind of small scale convection and mixing within the clouds are to kind of create new ice nucleation, and also kind of more mesoscale circulations between the cloud and the clear sky environment. So a lot of these things come down to ice microphysics and assumptions about ice crystal shape that affect radiative heating and all these sorts of things that are parameterized, I think, quite differently. And probably, if I had to guess, kind of all those things together are just adding up to a lot of uncertainty here. And then when you multiply that change in area by the cloud radiative effect curve, which is a little more constrained between all the models, there's still some differences in the CRE for a fixed ice water path across the ensemble. But so you're kind of multiplying these two things that are both uncertain, so you end up with just a much wider uncertainty, and there are kind of some non-linearities of models producing increases in cloud amount that tend to have the most positive radiative effects, so you get kind of some multiplying effects there. So that I think is what's driving the uncertainty there. And then the next question,
what's the diurnal cycle?
Diurnal cycle, yeah.
You take that into account?
That's a great question. Yeah, so no, we haven't. So these runs are all done with kind of constant insolation that averages out to the annual mean in the tropics, but does not have a diurnal cycle. And yeah, like you said, I think there's some work showing that the diurnal cycle does matter for how Anvil clouds evolve. So I know of some work that Blaz Gasparini led about that, where we kind of did these simulations launching different Anvil clouds at different times of day and seeing what their kind of cumulative radiative effects were. I think the results were nuanced. There wasn't like a clear takeaway that I have in my head to say, but I think, yeah, that's a good point to consider going forward. I think, yeah, I don't have a good intuition for kind of in which direction that would affect things here.
Wonderful, thanks.
Great. Oh, we've got a question from Eric DeWeaver, which I'll read out as well. Do you think the thin cirrus has a large component from adiabatic cooling in the ascending phase of TTL gravity waves? I assume that would imply less sensitivity to warming-induced changes in convection.
Yeah, that's a good question. I think, yeah, definitely we know gravity waves play a big role in these thin cirrus. So I think, yeah, so I guess I'm unsure how much thin cirrus we are capturing in this ice water path framework. We have a lower cutoff here of around 1 gram per meter squared, which I think some gravity wave generated cirrus can get up to that point. But I think the really kind of thinnest subvisible cirrus that are kind of ubiquitous in the TTL are generally going to be a little lower than this. One thing, I guess, even if we were to take those in account, their radiative effect is so weak that I think our kind of end result is not going to change very much, kind of whether or not those clouds change at all, or if they increase or decrease, the radiative effects of those are pretty small. So when it comes to the clouds that are radiatively active enough to make a difference here, I think most of them seem to be associated with deep convection. If you kind of look at snapshots of these models and you look for the parts that are covered in the amount of ice we're kind of considering here, they tend to be clustered around these deep convective cores. So I think most of the effect we're capturing is related to these convective systems. But yeah, I think that would, if we are capturing some gravity wave cirrus, that could be an additional reason why we're just not seeing much of a response to warming at those lowest ice water paths.
He says, thanks.
Thanks, Eric.
Yeah, I think we're running a little, we're over the hour now, so I think we should just thank our speakers again for the great talks. And we make the chat will be available afterwards. I know Antonietta was furiously answering questions in the chat well. So those will be available for those interested. And yeah, I actually have one more question while you're still here, Adam, actually, which is, so there's a lot. So RC-EMIP phase 2 is coming up, or at least, there's a protocol paper out, and it seems like there have been a lot of RC-EMIP studies which have kind of got to a certain stage and then be like, oh, there's no diagnostic, we don't have the diagnostics we need or the variables we need to, kind of really dig much further. So if you had a wish list, what would you have liked from RC-EMIP phase 1 to like help you get a bit further with, say, the microphysics or something? This is my spicy question. Sorry.
Yeah, that's a great question. I think, yeah, so in terms of like diagnostic tools, one thing that I know is already in the works and has been published in part is kind of developing kernels for these models, so you can do a more formal feedback analysis, which Catherine Stouffer of Florida State was working on, and they just published some results for the first phase looking at these small domain experiments. I'm not sure they've had the chance to apply them to the larger domain ones yet, since it's a lot more output and involves a lot of offline satellite simulation, and it's no trivial task. But I think having a set of kernels like that would, of course, be great to kind of look at a more formal feedback analysis in each of these models. When it comes to output, I think some sort of microphysical quantity would be useful. I think we have mixing ratio like you would expect when it comes to kind of really getting into the nitty-gritty of the radiative feedbacks. And if we want to develop these kernels, having something like ice particle size or something like that would be really useful, just for kind of I guess cutting back on at least one big assumption you'd have to make to do these satellite simulators and a more kernel-based approach. Yeah.
Cool.
Yeah, looking forward to the next phase of that.
Yeah, exactly. Cool. Sorry, I took speak, like, organizer's privilege, keeping you past the hour. But yeah, thanks again to Adam and Daeho and Antonietta for the great talks.
Thank you for the invitation. This was fun. Bye.